Hello and welcome back to another lecture for Computational Science 1. Today we're going to look into Newton's method for root finding. Before I dive into it, I want to let you know that I did go over bisection method last lecture, another root finding method, and I'll be referring to a couple things from there, so I definitely suggest you watch at least the beginning, since I won't explain in detail what root finding methods are, which I did that lecture just in the beginning. Now, without further ado, let's dive into Newton's method. And as always, we'll start with theory, or better said, a graphical example. So how does Newton's method work? The first thing you want to do is have an initial x guess. So you want to choose an x value, obviously, as close as you can to the root. And that would be your initial guess. So in this example, or in this graph, this is a simple function, which is... Here, let me write it here. This is simply just f of x equals x squared plus 1, I believe. And this might be half. I'm not too sure. Just from seeing where the root is, that looks like a half, x squared plus 1. But it's just a quadratic function, all right? And the root is right here, as you could see. Now, like I said, for Newton's method, the first thing you want to do is have an initial guess, as close to the root as you can. Now, obviously, for here, you can just say, oh, my initial guess is, let's say it's 1. For the example's sake, I'm going to choose 0.5 as the initial guess. So this is going to be my x0 being the first guess. All right? So the dot is going to be right here. That is going to be my f at x0. All right. Now, once you get your point, what you want to do is draw a tangent line. So I do have a little line here just to save us some time. And it goes something like this. All right. Now, this new root from the tangent line, this is considered to be your new approximation to the real root, right? So this is your initial guess. This is your new approximation. All right. Now, how do we find this new approximation? If you remember from calculus or from math, the slope of a line is just rise over run. Okay. So let's first draw a quick triangle. So I have this. There you go. And so here, what we have is rise over run, right? This is how we can get the slope of this line, okay? In other words, the rise over run is simply the change in y over the change in x. And if you remember now from calculus, the change in y over the change in x is equivalent to the derivative of x. The derivative gives you the slope, right? So what does the change in y represent, and what does the change in x represent in this case? So obviously, this right here is our change in x. And this right here, that's horrible. There you go. This right here is our change in y. Now what I want to know where my x1 is. In order for me to find x1, I can simply do... Wait, what is this line that just... Oh, never mind. Oops, I got tripped out. But in order to find this x1, what I could do is x0 plus the change in x gives me x1. So let's do that. How do I get my x, the change in x? Obviously, we have this function right here. All we got to do is rearrange, and we will get root of x equals the change in y over the derivative. Oops. There you go. So now that we know, well, for the derivative, you can simply just derive the equation and you get your derivative. For the change in y, what exactly is that? Well, that is simply just the function. F, whoops, actually, I'll keep it and I'll write it again. That is simply the change in x equals f of x divided by the root. Or not the root, the derivative, right? So if I take my x0 now, I plug it in here, and then I take it and I also plug in here, I divide the two, that will solve for this. Now, since I have this, like I said, what I can simply do is x0 plus the change in x. So I'll start up here. x1 equals x0 plus the change in x. Okay? In other words, I could sub in everything, and I get x1 equals x0 plus the function at x all over, and this is obviously x0, all over the derivative of x0. All right? Now, there's one small problem with this, is that right now, my derivative, this line right here, is negative. So this derivative here yields a negative. So what I'm actually doing is x0 minus this fraction, which in return doesn't give me this x1, it gives me x1 in this way, right? Now that's problematic, so all we gotta do, instead of adding this, we can simply change it to a negative. There you go. Now that solves that issue. Now you might think, okay, well, if the derivative here is negative, what if the derivative is positive? Well, if the derivative is positive, right? Here, actually, let's continue with this example. So we do two things at once. One is we show how we're getting close to the root. And two, we show why this is negative and it works for positive derivatives. So I'm going to remove all this since we got our new approximation now. There you go. We don't need any of this stuff anymore. And we know that, oops, and we know that this is my x1. Now let's iterate the second time now. Now this obviously, well, I can't really catch this down here. So what I'll do is I'll do a quick drawing here. I'll do it here. So let's say this is our first x0. The reason I didn't choose this point to begin with, because I wanted the triangle to be big enough so you can really see what's going on. But now that you saw that part, now we will choose something like this. So there you go. That's going to be my tangent line. Trying to really make it good. There you go. So this is going to be technically my... No way. No! I messed that up. No shot. There you go. We'll just do this way. So now this is right here. That's my new x1. Now I'm going to remove this approximation and iterate the second time. Okay, so iterating the second time, this is going to be my new dot, right? And now you see we're getting closer. We're getting so close to the root. See, this is what it looks like. And now obviously this dot right here, this is going to be my x2. And then you keep approximating, and then you'll get closer and closer and closer to the actual root. Because if I really try to zoom in, there is a small triangle here. So obviously we can't really see here, but you keep approximating, you keep getting closer and closer to the root. Now, why is, if this derivative is positive, this still works? This negative part here still works. Because if this is positive, this is now my new x, right? So this goes, so now we get rid of these. and we get rid of this. Now what we're trying to approximate is 2, 1, and then we have 1, right? So now x1 is here, okay? The derivative is positive. So what we're doing here is the change. This is the change, right? So this is our change of x. The change is this whole part, and it's positive. So when I do x1 minus the change, which is what's here, that goes backwards now, which is where x2 actually is. So that's why having this as a negative, when the derivative is negative, it goes forwards, and when the derivative is positive, it goes backwards, which is, how it's supposed to be. And so that's basically Newton's method, and you keep iterating over and over and over again until you get an answer. Now, there is a couple catches. It's not as perfect as it looks, all right? And that's what we have here. We're going to go over pros, cons, code, requirements, and error. So for the pros, it's just as simple as it's fast convergence. So it converges quadratically. And fun fact, this is the fastest method out of all the methods for root finding. Okay, now there's a couple cons. The initial guess is sensitive. So one is steep gradient. How does that work? Let's get rid of all this stuff now. We don't need any of this. Whoops. All right. Jeez. So why does steep gradient not work that well? That is because if my function, let's say it's like something like this, right? And you try to, here, let me make this even better than that. That's horrible. Let's say my function is, there you go. We'll have it something like this. So when you try to choose the dot, let's say the dot is here, and then you approximate this line, and obviously this goes all the way down. Your new x1 is going to be so far down, right? Because you want to approximate this down like wherever this line goes, and it's so far down. So this will have the first issue. Now, let's say you know your function, and you choose something even smaller. And so you'll go like, oh, okay, I'll get closer then, and I'll choose this dot. That you still have the same issue here. You see, this is your new x, and you can't really approximate this because this will go straight down, let's say, like it's an asymptote. And so that's why steep gradients don't work. Now, another thing that doesn't work is, what did I write here? The derivative of 0. So if you choose your initial point, the very initial point, to be here, let's say, obviously when you're choosing, you don't really know this, but if the derivative equals 0, right, when you try your tangent line and the derivative equals 0, once this never goes to the axis, so the x-axis, so you never really are able to calculate it, and hence you actually get an error, because the equation, if you remember, for the change of x, it's f of x divided by the root, divided by the derivative. If the derivative is 0, you can't divide by 0. So this will give you undefined. All right? And so these are the two issues that you will run into, is that steepness and derivative cannot be 0. All right? Another con is obviously need derivative. For example, bisection doesn't need derivative. So some functions are hard to derive, or they're very, their derivative is computationally expensive. So that's one of the problems. Also, the zero derivative problem that I mentioned earlier, up here, that is one of the problems because you cannot divide by 0, right? So the requirements in order to use Newton's, it must be continuous. But if you remember from bisection, we said it must be continuous within the interval. This one, we don't have an interval. So what we'll say is, well, it must be continuous and differentiable around the root or the initial guess. So remember when I was like working, when I was like had a guess here, and I was working with this whole area, everything I was using was kind of like within this section, and I never really left it. Even when you get your new approximation, this becomes like that, and then you start getting closer to the root. So what you need is differentiable and continuous around the root and around your guess, but it doesn't necessarily have to be the whole function. You just got to make sure like around the area that you're working with, it is differentiable and continuous. And like I said, non-zero derivative. So for example, one example you can run into is, what if your function was something like, there you go. We'll have something, or actually, we'll do something like, I can do a better job. So, oh wait, actually I can use this. Okay, so remember how I said your initial guess, if it's here, you'll get 0. Now, what if you choose your initial guess to be on this side? Well, one, if this, well, actually, I will have to draw another one. Let's actually copy this. But let's say on this end, it just goes like this and never meets. If you choose it on this side of the function, this will not converge, or will falsely converge. In other words, it could also diverge, because this will, well, this never. So if I choose it here, right? If I choose that, thing is, my freestyle drawing is horrible. So if I choose this and I'm trying to find this root right here, obviously this will be like, oh, this is my guess, and then it will, use this as one point. So let's use black. Let's say it chooses this as the guess, therefore it will use this as my new x1 and keep trying to converge, but it never converges. That's one issue. And the second issue, so that's when you have a horrible guess. The second issue that I was drawing earlier is, what if your function was something like, how do I want to draw it? I think this is, I'm going to draw a sine x minus x, which I believe goes something like this. Okay, so if you do choose like something here, obviously this obviously won't converge, because it will eventually go down here, and that's a 0. That's a derivative of 0. So that's another thing that you might run into. So you really need to know what you're choosing and keep all these aspects in mind. So you can get non-zero derivative even though your initial point is a non-zero, right? Your initial guess is not a 0 derivative, but eventually it gets to a 0 derivative. So you got to make sure that doesn't happen. And obviously all this depends on a good initial guess. All right. Now for this error, I went exactly over this in the very first lecture called Error and Tolerance. It's a 20-minute lecture. I went very in depth of how these exactly work. So I'm not going to waste your time again. All you need to know is that this is simply the change in x, which is what we were using as the error. All right, this is basically your current guess minus your new approximation, like your initial minus the approximation. I try to keep it pretty just because like I hate clutter. So the steps to do Newton's is just simply choose an initial guess, iterate using this function. And so basically what you'll do is, this is going to be your initial guess here. This will be 0, this will be 0, this will be 0. You'll get your x at 1. Then you'll look for x at 2, and then it will switch. This becomes 1 minus f at x1 over f derivative at x1. And then obviously you find your x2. Your x2 gets plugged in, and then this becomes x3, and you keep going and you iterate. After each iteration, you usually want to check for your error and residual, which again, I explained in lecture 1. If you don't understand it, go check it out. Now, to go over the code, simply what you'll want is obviously the function you're working with, the derivative of that function, the initial guess, your tolerance, residual, and your max iteration. Now, when you do it by hand, there's no max iteration. You'll stop when you want to stop. But for code, obviously, we want to avoid infinite loops. So we have a max iteration that we pass to the function, to Newton's method. So the first thing is you want to just initialize variables. Your x is going to be the initial guess, and you're going to have a convergence variable that is a Boolean, true or false. Then we're going to start an iteration that goes from I to your max iteration exclusive of your, so if your max iteration was 100, I believe this will go from 0 to 99 excluding 100, or from, I'm not sure exactly the exclusion part. So I should probably check that out. But just keep in mind that there is some weird things in Python. Thing is, no other language does it except Python. That's why I'm kind of like, but yeah, please double check that. But yes, it does go from I to your max iterations. Your R is simply the function at the current guess. So when you first start, it's the initial, but eventually that x variable will change to either x1, x2, and so on. You calculate the change. The reason we make this negative is, again, I removed the equation. It's right here. It's due to this negative, right? So simply we put negative f of x, or in other words, since we made x r, we can make this simply r. All right, divided by the derivative. After you do that, you take the current, so this is my initial guess. You can assume this is x0, and I add whatever this is. Well, technically you minus, but that depends. If the derivative is positive, this becomes, if the derivative is negative, this becomes positive. If the derivative is positive, this becomes negative. So when you add it, if this is negative, it subtracts. If this is positive, it simply goes ahead with the positive. All right, and I explained why this works just like a couple minutes ago. Then you check your condition. If the absolute change of x is lower than the tolerance and the function at x, the absolute function at x is lower than the residual, that means you converge. Again, I explained this first lecture, 20 minutes. If you don't understand it, go watch it. That's when you'll converge. Therefore, you break. If it doesn't, remember here, this was something like this. So as you can see, my x variable that was up here changed, and now it shifted to x1. And so when I don't converge, when this condition never runs, I go back to the for loop and I run again with my new x. So this x, you run again with the new x. So this becomes x1, this is also x1, and this is the new change, and this now turns into x2, and so on until you either break or you finish your max iterations, which by then, whichever happens, you'll return your x value, which is your approximation. This is your approximation. This is your error. This is your residual. This is your residual at your approximation. This is your error at your approximation. And this is whether you converged or not. Because if this condition runs, you will converge. But if this condition never runs and instead you hit the max iterations, you will still return whatever you got, except this will be false because it never turned to true, right? And that's about it. That is Newton's method. I hope this video helped. In the next video, we're done with the root finding for now. In the next video, we'll be going into linear algebra. We will be writing an algorithm that solves matrices in row echelon form. So, or reduced. No, yeah, it's row echelon form. So I'll see you guys in the next video.